We'll first have a short talk and then 2 long talks. First talk is improving MPGAA star for extended visibility ranges.
Hello, my name is Carlos Hernández. I'm going to present this work that was done with Jorge Baier from Universidad Católica, and I work in the Universidad Andrés Bello, both universities in Chile. Okay, in this presentation, I'm going to present an improvement of MPGAA star algorithm, and the talk is have 4 parts. The first part, I provide you some background. Next, I'm going to present the motivation of this work. Then, how we implement the motivation, or how we implement the improvement, okay, of the algorithm, and some results at the end of the talk. Okay, the setting that we work is pathfinding in general graph. In particular, we are interested in dynamic terrain. That means that in the graph, the arc cost can increase or decrease while the agent is moving, or while the robot is moving in the terrain. Okay, this is an important problem, we think, for robotics and for other applications. And okay, what is MPGAA star? The name of the algorithm is Multipath Generalized Adaptive star that we present in IIIA in 2015. It's a very simple modification of a previous algorithm that's called is Generalized Adaptive star from 2008. And this algorithm outperformed the starlight, the state-of-the-art algorithm, in several settings, and is simple to understand and optimal, like Generalized Adaptive star and the starlight. Okay. Okay. What is the main idea of MPGAA star? Specifically, what means MP? MP means multipath. Okay, and the idea of multipath is that, suppose that the agent is in these cells P3, and the wall cell is B9, and the range and the visibility range is 1, and the agent only can see these block cells. Okay, the agent, the robot, perform a search. Okay, and when the agent moves in this part, this cell become blocked. Okay, but however, this part, some part of the previous shortcut path is still valid. Okay, it's a shortcut path, and there we have one path. Okay, after, and what is the idea? The idea is that we can reuse this part of the previous search. For instance, in the second search, the search stopped early in this part because we have this part of the search. We have the previous search. Okay, we keep the previous search, and so on. Okay. For instance, in this part, is multipath because we have the algorithm generate a tree routed in the wall from many paths. For instance, yes, we have there search tree, and in this part, for instance, in this search, the agent only expand one cell to catch the previous shorter path. Okay, and this is the main idea of MP multipath. Okay, and this idea is implemented in over G adaptive star, generalized adaptive star, and the changes are in red. Okay, the changes are very small. This is why we say that it's a very simple modification of the previous algorithm. Okay. And here we have the motivation. Now, here I'm going to present a GAA in action. Okay, the agent is in this cell, the gold cell is that cell, and the red arrow are the visibility ranges. In this case, the agent can only see two-step look ahead, excuse me, 2 steps ahead. And in the first search, after the first search, the agent updates the heuristic. That's the green cells. Okay. This part is the part of the algorithm. The agent updates all the heuristic in the closed list after the search, in order to do the or to obtain a more informed heuristic. And when the agent is here, this cell is blocked, and the agent needs to replan. Okay, the agent replan and update the heuristic after the search. In this part, for instance, this cell becomes unblocked, and in this part, GAA star called other procedure, that is reestablish consistent procedure. That is a kind of Dijkstra algorithm that repair all the heuristic that was inflated. Okay, in order to maintain the consistency of the heuristic. Okay, what is the problem here? The problem is that a GAA star can update several non-relevant states for the current search. For instance, the current search or the current optimal path is this, but generalized star can update this heuristic, for instance, and this is not relevant for the current search. And in a more extreme example, we can have these things, for instance. Okay, in this case, the agent is there. This is the goal state, and okay, there if the visibility range is 2, the agent don't do nothing, because they don't see the change in the grid. But if the agent has a bigger visibility radius, he knows that this state change, and they update all the heuristic in this part. Okay, and this is a very expensive procedure, and the motivation of our work is to update only relevant state for the current search. For instance, this is an ideal work in order to reach the goal. Okay, and how we implement this idea? Okay, first two important observations. Admissibility is not required for obtain optimal path with A star. That means admissibility in all search space. Because if we have admissibility in this state, okay, we can calculate an optimal path. Okay, and still optimal if every generalized state, if for A star, well, it's still optimal in this case. Only when the generalized state for A star are admissible. Okay, and we did some two small modifications to the algorithm. The first, we don't call reestablish consistent from the main anymore, because if you see the algorithm, this is called here. Okay, each time that the environment change, this procedure is called. Wow, sorry. And we call from the main, we call the procedure during the search, so during A star. Okay, and we use this procedure, that initial state, that this procedure is called each time that a state is generated. For instance, this is A star, and this procedure is called in in the initial state and in each generated state. Okay, and in this manner, the idea here is to do instead of to do eager updating, we use a lazy updating of the heuristic, and we update the heuristic only when we need to update the heuristic. This is one of the motivation here as well. And yes, and to do this, to limit the update of the heuristic, we update the heuristics only when in the state that have an heuristic, or we run the established consistent procedure only while the heuristic is lower than the heuristic of the current state of the agent. Okay, and here we can see an example. Okay, here we have many things, but here we can see an example that only update the consistent procedure, only update this 4 state instead of all this state in the previous example. Okay, the algorithm is optimal. You can see this in the paper, the theoretical results. Okay, I'm going to show you this. I think this is better, it's more clear. For instance, for GAA star, this is the total expansion that the agent do, and for with the improving the number of expansion, we reduce the number of expansion. This difference increase when the visibility range increase. And for the MPGAA star, we obtain better results. Okay, we reduce an amount in a big amount the quantity of expansion. Okay, and the results show that we run very fast regarding the previous algorithm. Okay, and in several settings are faster than the starlight and A star that run from scratch each time that the environment change. Okay, we present a simple improvement to MPGAA star that allow more efficient update when visibility range are higher. We outperform our previous version of the algorithm and outperform the starlight unless visibility range larger than 1,000, because we do some experiment. We did some experiment when the agent can see all the environment, and in this case, the starlight performed better than MPG star for omniscient agent. Okay? And at future work, we plan to do application in robotics, or to apply this algorithm in robotics. So, thank you.
Any questions?
So I think I may have missed something. So you are reducing the number of updates that you do,
yeah,
of the heuristic updates. Why does that translate into less expanded states?
Because each update is an expansion as well.
Oh, each update is an expansion.
Yes. Okay. We plot in expansion. We plot the expansion that do A star and the expansion that do the update procedure.
Thank you.
Any other questions? Let's thank the speaker again.
Thank you.